Okay, so we'll go ahead and get started. So welcome everyone. I'm Tony Ramajan. I'm the interim director here at the Green Bank Observatory. I just got a couple of updates from the observatory before we get started with our talk today. So if you've been on TV or watching internet, watching the Facebook, watching the Instagram, whatever your favorite social media's account is, you will notice that we have opened up a brand new era here in the West Virginia radio astronomy zone, as we're offering 2.4 gigahertz Wi-Fi to the Green Bank Elementary School. So that was the big thing that happened over the course of the last week or so, as we presented our findings and our reports of all the analysis that we did and the impact of 2.4 gigahertz Wi-Fi. We're just pleased to announce that the school will be able to use that, as well as the surrounding community, for educational purposes that they need at the school, because it was the only school in the entire county that wasn't actually allowed to use Wi-Fi because of its proximity to the Green Bank telescope. But I think this is a good thing that we're doing, allowing that Wi-Fi access to the school, because we want to, of course, drive forth that importance of STEM education and working with our community members in order to give the absolute best opportunity to our community, and especially to our students. So that's the big news that happened in Green Bank over the course of the last week. A couple other things that have happened: painting is done, so they're just doing final touch-ups to the telescope now. But there's a bright white part of the top of the feed arm. So if you want, next time you come out to visit the Green Bank telescope, you could check that out. Next up, replacing some worn out wheels, changing the oil, replacing the wiper fluid. Those last two are jokes. Proposals are under the technical review right now. So thanks to everyone who put in a proposal last month for semester 26A. And preparation has really started for our return to operations. So we're now seeing, as we go over the next several months or so, putting the receivers back on the telescope, getting ready for operations, which should start on or around the end of September, around 26th of September. So if you do have a 25B program that still needs to be set up, start working with your project friend now and make sure that it's ready to go when we turn to operations near the end of September. So that's all I have for announcements. So I'd like to hand it over to Jay, who will introduce our speaker today.
Thanks very much, Tony. Our speaker today is Steve Croft from UC Berkeley, Oxford, and the SETI Institute, and he'll be speaking on updates from the Breakthrough Listen Technosignature search. Let me remind everyone to submit your questions through the Q&A button at the bottom, and we'll get to them when Steve's done talking. Steve, take it away.
Thanks, Tony. Thanks, Jay. Thanks, everyone attending. So I'd like to give you a little bit of an update on what's been going on in the search for technosignatures, or signs of technology as a proxy for intelligent life beyond Earth. This topic, as many folks are aware, has a long history at Green Bank. Frank Drake was one of the early employees, arrived in 1958 at GBO, and he used the 85-foot Tatel telescope to undertake Project Ozma, one of the first modern searches for extraterrestrial intelligence. Frank undertook this search by essentially borrowing time on some other equipment that was being used for some Zeeman observations. You can see in the log on the left here, Ozma marked down in April 1960. And Frank had a single 100 hertz channel, which he tuned over a 360 kilohertz bandwidth to look at two stars, Tau Ceti and Epsilon Eridani. And in one of those observations, as they were looking at one of the stars, they saw a signal. They thought, wow, could it be this easy that we can find signs of extraterrestrial intelligence? And they did some further investigation, including hanging a horn antenna out of the window of the control room at the 85-foot. And when they saw the same signal coming in from that horn antenna, they realized that it was RFI, radio frequency interference. And so this has been sort of a plague for SETI searches, and of course for radio astronomy more generally since the beginning, really mitigating RFI, understanding the RFI environment, and RFI is sort of the motivation for our searches, the fact that we all do have these devices ourselves, and that we have now just such an increasing number of electronic and transmitting devices that contribute to the RFI environment, making this more challenging, but also motivate us to look for signs of technology elsewhere, potential transmitters that may have originated from intelligent life on other worlds. We have a little bit of an upgrade since Frank did his first experiments with that 100 hertz wide channel on the 85 foot. We now, of course, have the GBT, 100 meters in diameter, and we have the breakthrough listen backend. I'm not going to go through these stats in detail here, but essentially we have a billion channels with 3 hertz resolution, actually several billion channels with 3 hertz resolution per channel, petabytes of storage, and we're looking at thousands of targets. So, incredible advances, particularly in just the Moore's law availability of computing power, which has really driven these advances in the technology, of course, of the GBT and its receivers. So here's a little zoom in on the radio spectrum. You can see helpfully that radio astronomy has been allocated a little chunk of the spectrum between 1400 and 1427 megahertz here, covering the hydrogen line at 1420 megahertz. And the little red line, I'm not even sure if you can make it out on your screen here, but I put a red line, and that's actually a box which covers that range of frequencies, that 360 kilohertz range of frequencies that Frank observed during Project Ozma. And as I mentioned, now the situation has changed. This is just the frequencies covered from L through X band from 1 to 11.2, or actually now up to 12 gigahertz with the GBT's suite of receivers. And Breakthrough is also extending this to higher frequency receivers with Ka, Ku, and KFPA that will be engaging with in earnest when we're back online in the fall. And so this is an amazing advance, but as you can see from this frequency allocation chart, it also means we have to contend with RFI from a whole range of other transmitters. So I have a student working with me this summer, Andres Luengo, and Andres has looked for essentially just signals above some multiple of the noise in the breakthrough listen observations going back to 2016. And you can see here we're scrolling through the spectrum from 1 up to 11 gigahertz. And a lot of the RFI that you're seeing here, particularly the stuff at 4 and 11 gigahertz, you can see in this sky plot is located towards the south in the geosync belt. And so, this is an issue for us in terms of kind of the scales that we're looking at, sort of on hertz to a few hundred hertz frequencies. We don't appear to be quite so badly affected by Wi-Fi, fortunately, which is maybe good news given the recent updates regarding the school there in Green Bank. And I think that's in part because this is relatively broadband compared to the scales that we're working at. We do see a bunch of RFI at L-band, particularly from things like GPS satellites, which is a challenge for us in terms of our the hits that we're getting from our data. So how do you deal with the fact that there's this RFI that is sort of the haystack in which we're looking for the needle of our signals? Well, you do sort of something similar to what Frank did in terms of that initial interference rejection. You look at the target that you're looking at, and then you look somewhere else. And then we look back at the target again, in this case, Vega in this animation. Then you look off at another secondary star. You look back at your primary target for 5 minutes in our GBT observations, and you look somewhere else. And you can see as we swing around here to another region of the sky, we're now looking at a different star. But the geosync belt there, we're not really hitting the same targets in terms of those satellites because the sky is moving relative to the as-L positions, the static as-L positions of the geosync belt, and then stuff that's in LEO and low Earth orbit is also moving relative to the stars. It's moving at the sidereal rate across the sky. And so if we see a signal in 3 successive on-source scans that we don't see in the off-source scans, then we can be more confident that it's not potentially a SETI signal, but that it gets through that initial filter and is looked at further. Another method that we can use to try and filter out local RFI is that local RFI has a higher tendency to be at a static frequency, not to be changing in frequency over time. And so if we look for signals that are Doppler drifting, that's the characteristic that we'd expect from a transmitter that is potentially located on a rotating planet or in orbit around another star, and then is picked up by the GBT, which of course is on a planet that's rotating and rotating around our own sun. And so this introduces not just Doppler shifts, but Doppler accelerations, which manifest as drifts in frequency in the spectrum. And we can leverage that to, again, try and filter out any nearby interfering sources. And so the combination of these two techniques enables us to plot spectrograms like the one shown here. And so this is 6 scans, again, 3 scans on target, interleaved with 3 scans off target. So I can illustrate this here: on, off, on, off, on, off. So 5 minutes on target, 5 minutes off. And you can see the red line that's sort of guiding your eye in the center here that's been just added afterwards on top of the spectrograms. But it's illustrating that the algorithm has found a Doppler drifting signal here in the first scan. It's then projecting that drift rate down through the remaining 25 minutes of this cadence, as we call this set of 6 scans. And you can see there's a slight deviation from linear here. So, this is interesting in that it passed the Doppler drift filter, but it fails this spatial filter. It's not spatially isolated on the sky because the yellow signal here in the middle here is visible in both the on scans and the off scans, so this gets discarded. But here's a good example of a candidate technosignature. This was found by a high school teacher working with me a few years back, Ilan Levy. And here you see the Doppler drifting signal visible in the on-target, gone in the off-target scan, although there's some broadband RFI there that's visible in the first off scan, back in the second on, gone in the second off, back in the third on, and gone in the third off. And so Ilan got pretty excited when he brought this to me, and I said, well, congratulations, you have found a genuine bona fide technosignature and breakthrough lesson data. It's not aliens. It's the Voyager 1 spacecraft. And so Voyager 1 is at a distance of 20 billion kilometers, has a 23-watt transmitter, but it's hooked up to a 4-meter antenna. And so this looks like a 1 megawatt transmitter when it's picked up at the GBT. So we pick it up loud and clear with the GBT in our data. And it's a nice sort of proof that our algorithms work, that they're able to filter this out and present it as an interesting signal from the background of RFI. In fact, this is such a good example that we actually have a Python notebook that we make available to our interns as they're getting trained up to use GBT data and to understand how the breakthrough lesson backend works. So Voyager 1, again, so pretty faint, although it appears like a 1 megawatt transmitter. Sophia Sheikh had a nice paper earlier this year when she looked at how far out these kind of technosignatures could be detected using sort of Earth circa 2025 technology. She used the SKA1 mid as an example receiver, but you can redo these calculations for GBT. And for Voyager 1, you could find it out to a distance of, I think about a light year was the number that they came up with in their paper. For atmospheric technosignatures and indeed for biosignatures in atmospheres with the sort of current and next generation of optical and infrared telescopes, you could find biosignatures out to a few parsecs. And so, there's only really a sample of a handful of stars that are amenable to investigations for signs of life, be it biosignatures or atmospheric technosignatures, that are going to be within range even of the next generation of spaceborne telescopes that are designed for this purpose. But with something like powerful radar, so the Arecibo radar illustrated here, which appears as a 10 to the 13 watt transmitter, given the width of the dish. Obviously, Arecibo no longer in operation, but one of the most powerful transmitters. If you find yourself in that beam, looking like a 10 to the 13 watt transmitter, could be picked up at distances of a considerable fraction of the distance across the galaxy, even by the current generation of telescopes. And so this is motivating us to do the kind of searches that we're doing in Breakthrough Listen. You heard a little bit earlier this year from one of my students, Caleb Painter, undergraduate student, finished up his undergrad now, heading into grad school next year. So Caleb used a slightly different algorithm. Rather than just looking for narrowband Doppler drifting signals, he used a kurtosis-based algorithm to look for signals that were present in the on observations and absent in the off observations. He found some examples like the ones shown in the bottom right here. And he was able to do this for over 2,000 stars at L, S, C, and X bands, and so covering 1 to 12 gigahertz with the GBT. And this is one of the most comprehensive searches to date in terms of putting limits on the prevalence of transmitters around nearby stars at those frequencies. Another student of mine, Carmen Chosa, now in the PhD program at Oxford University, also gave a talk in this webinar series about a year ago. And Carmen looked at nearby galaxies with the GBT. And here, certainly for a lot of the smaller or more distant galaxies, you can fit the entire galaxy within, or the majority of the galaxy within the GBT's beam at L band. Not so much at the higher frequencies, but at L band, you're encompassing potentially tens or hundreds of billions of stars at a time with the GBT's beam. Obviously, the transmitter powers required here are enormous for intergalactic distances, but we're putting constraints on these kind of transmitters across many billions of stars at a time. And so if you combine these constraints, as Caleb did in his paper from earlier this year, you can see the points on the top left here from Caleb's paper. So essentially this plot is showing EIRP on the horizontal axis, so how bright the transmitter appears. Again, Voyager 1 at about a megawatt is off to the left of the plot here. Arecibo's transmitter at 10 to the 13 watts EIRP is shown as the leftmost vertical line, and then type 1 and type 2 Kardashev civilizations as the two dashed lines here. So we're basically putting limits on, from Caleb's work, the prevalence of Arecibo-like transmitters around a couple of thousand nearby stars. And so the transmitter rate, which is shown on the vertical axis here, shows things that are relatively common up at the top, things that are relatively rare down to the bottom. And again, the horizontal axis is showing faint things off to the left and bright things off to the right. And then Carmen's work on the nearby galaxies is represented by the cluster of circles that are around 10 to the 24 watts EIRP, so hugely bright transmitters here, but we're able to probe something like 10 to the 12 or 10 to the 13 stars. And so this gives us a rate constraint on transmitters that are far rarer than we can get from the nearby stars. And so we're ruling out the region in the top right of this plot, but the region to the bottom left of the plot is still underexplored. So we need to look at more stars with higher sensitivity in order to probe this region. And again, the constraints that we have currently from the nearby stars are for sort of fewer than one Arecibo-like transmitter pointed in our direction, always on at the frequency band that we're looking at, about per 1,000 stars or so. But what if we're missing stuff? I like this cartoon from New Scientist about a professor who discovers that messages sent across the universe by alien civilizations have all been going into junk mail. And so, maybe we need some different algorithms. And as an example of one of those algorithms, I wanted to talk briefly about autoencoders. So here is a set of handwritten numbers from the MNIST dataset. And you can see by eye that even though there's some variation in the way that people write their numbers, there's still more things in common between different variations on a number 4 than there are between a number 4 and a number 9, for example. And so what we do with an autoencoder is we feed in this sort of toy example, these numbers into an encoder, which gives us a representation in what we call a latent space in the middle here, this sort of abstract vector space. It's then passed into a decoder, which gives us, if we've done this correctly, the same number or a similar representation of that number out on the right-hand side. You might think this is sort of trivial. Why would we want to feed pictures of numbers in and get pictures of the same numbers out? The reason why is that by minimizing something called the loss function, which is the difference between the output and the input images, we can be confident that our representation in this compressed latent space in the middle here is a good one of the input. And then we can do clever things like looking for similarity between different images or different inputs in the latent space in order to cluster them, in order to look for anomalies and outliers. And that's what we've been doing quite a lot with breakthrough listen data. So our former student, Peter Ma, he's now a grad student at UC Berkeley, injected some signals into these cadences. You can see in the top left here an example of a signal which is not a good SETI candidate, and then in the middle there, one that is relatively good. And Peter was able to train an autoencoder with these simulated data, and then to use this to pick out real examples in the real data that looked like the kind of SETI candidates that we're interested in. And he found some signals. They didn't reappear in follow-up observations, but it's an interesting technique to add to our arsenal of techniques. Peter was able to use a similar tool to do a reverse image search. So if you see some particular signal in your data, can you then match that and find other similar signals that are close together in latent space? Can this help you understand the RFI environment? Can it help you understand whether a signal that you're looking at is truly anomalous? Again, this is something that we'll be deploying more going forward. And then my student Ben Jacobson Bell computed some statistics on some of these examples that were found by our narrowband Doppler drift search pipeline TurboSETI. So he computed 13 statistics on these and then used those statistics to perform a clustering analysis. And again, was able to find, as you see in the example on the right here, examples of morphologically similar RFI at a range of frequencies that then can help us throw out some of this RFI that makes up the haystack in which we're looking for the signals that we're interested in. One other example here by a grad student, Sneer Pardo, uses a different method looking for cross correlations between the spectrograms in a cadence. So you see on the left plot here an example of a signal that's present in both the on and off observations. In the center, an example of a cadence that mostly just contains background noise. And then in the right, a signal that might be interesting to us. And so what Sneer did using a technique called UMAP, was to cross-correlate all of these individual scans with each other. So you end up with 15 pairs essentially in this 6-scan cadence. And then again, by injecting signals and in this abstract latent space here shown in this UMAP plot, he's able to identify the regions that correspond to cadences that only have signals in the on scans and that don't have them in the off scans. And I think I've mislabeled these actually in this plot. It's the green cluster here that you should be interested in, which is the only on target events. And then they're able to examine the top 1% of those signals. So here we're actually now comparing the position in another latent space of the on target scans, which are denoted A, with the off target scans denoted B. And the green example here is a good one where the A scans are morphologically similar and the B scans are morphologically similar. And so, but this is signals that are present in the on scans and not in the off scans. And so we're able to say we think this is the same thing that we're picking up in the on scans. So it's another way of kind of filtering through this. I won't get into this in any detail at all, given the limits of time. But colleague Vishal Gajar is also looking for pulse signals that are present using machine learning approaches. This can help us find candidate SETI signals, but also things like fast radio bursts are also potentially be used to look at pulsar signals. And we're deploying now these kind of FRB searches in a real-time system that's been deployed initially at the Allen Telescope Array in a collaboration with NVIDIA. But we're hopeful that we can bring some of these real-time detection techniques to our pipeline with the GBT. So that's all I have time for today, but I did want to just advertise our summer program. We're in our last week of our summer internship program at Berkeley. We have a great program with interns from around the country working on a variety of science topics, including several working on data from GBT. So if you are a student or if you have students that are interested in applying for next summer, applications open early December. And I will close with that. Thanks very much.
Thanks very much, Steve, for a most excellent presentation. We now invite questions, and please submit them through the Q&A box at the bottom of the screen. We have several already. The question, what integration time was needed to detect an Earth-like signal at 1 kiloparsec?
Yeah, I think that's so for the I'd have to look back at Sophia Shake's paper. I know for the Voyager 1 signal, they assumed an hour of integration with SK1 mid. So I don't think they're going to sort of unfeasibly long integrations. I suspect it's something similar for the signal from the Arecibo radar.
Okay, there's another question about our own march toward digital broadband from narrowband searches. And the question is, how's that affecting your work?
Yeah, so we have to date focused on narrowband searches, and I think the idea here is, the idea here is that I have to go through these builds again. If ET wanted to get our attention, then putting a lot of energy into a narrowband signal, if you're sending a deliberate beacon, is a good strategy. And as with Voyager 1 here, you're seeing the carrier signal from Voyager 1, so the data signal is off in the sidebands, but the carrier signal enables you to get a lock on Voyager 1. And so, even with digital communications, I think there's sort of still a motivation, particularly if you're deliberately trying to signal somebody and just say, we are here, to compress your signal in frequency and or time. But in approaches like Caleb's here, where he's using just kurtosis and comparing on and off scans, you see in the bottom right scan here, that's not sort of a classic narrowband Doppler drifting signal. This is somewhat more broadband. And so these kind of approaches, particularly looking at data at a coarser frequency resolution, are ones that we're exploring.
We have a question about whether slides from this talk will be available, and let me answer that by just pointing out that all of these webinars are available through the greenbankobservatory.org website, and this talk will be uploaded within a day or so. So yes, you'll be able to replay the entire talk. Another question, what are your plans for the GBT in the next few years?
That's a good question. I don't want to speak to sort of the overall strategy of the project because that's subject to the PI and the breakthrough initiatives that are funding us in terms of their plans for engagement with GBT going forward. But in the short term, we're planning to extend our searches to higher frequencies. I mentioned we've done some commissioning with the KU, the KA, and the KFPA receivers, and so we're interested in re-observing our samples, including the nearby star sample, with those receivers. We are interested in re-observing just some of the very nearest stars at 0 to 5 parsec sample because it's been a while since we've looked at those stars. We started off with those in sort of 2016 and 2017. And then I think, as I've illustrated in the talk today, another big thing that we're looking forward to doing is going back and both reanalyzing existing data and analyzing incoming data with more advanced algorithms, particularly powered by AI and machine learning.
Mhm. Here's another question. You're displaying right now a signal. What is the origin of that signal?
Yeah, that's a good question. We often have to sort of go on a bit of a deep dive with RFI and figure out, is this in a band that is that has a lot of interference in it. So for example, we do see a lot of signals, a lot of our candidates pop up around 1575 megahertz, which is one of the GPS frequencies. In part, I think just because of the density of GPS satellites on the sky, which happens to trigger our algorithms to find things on this sort of 5 minute on-off cadence just by coincidence. So we have to sort of look at the broader signal morphology. We have to zoom out in these kind of contexts, particularly where we see signals of interest like this. We see is this part of kind of a larger frequency comb? Are the lookalike signals? So we actually did have there was a lot of interest in a signal called Breakthrough Listen Candidate 1, BLC1, a few years back, including in the media. And we had to sort of do this kind of reverse image search that I mentioned that Peter Ma has been working on, although we had to do this sort of more manually at the time. And so the idea that we could look at a signal and then do this kind of image lookup in the spectrograms and see, is this something that occurs at other frequencies or in observations of other targets, that helps us rule out whether it's a signal that's truly coming from the target star or whether it's some common interference that's seen in the data. But I can't sort of pin this down in the particular examples that I showed. So it's quite a task, but we have improving tools to be able to do this.
Mhm. I have a question in that some of the results that you've reported are non-technosignatures, but clearly of astrophysical interest. Could you comment on some of those?
Yeah, that's right. So we've had some studies of fast radio bursts that have probed interesting substructure in FRBs. I should also note that the Listen backend is a very capable digital spectrometer that we make available to the community through the regular proposal call for 50 hours per semester as a shared risk instrument. So if folks on this call are interested in proposing, obviously too late for the most recent call, but please get in touch with me. There's been broad interest from the FRB and pulsar community in using the Listen backend as a spectrometer. We also were approached by some colleagues at UC Berkeley who realized, and I think actually I have a slide in my spare backup slides here. Whoops. And I just went one too far and quit out. 1 second. Let me reshare. Some colleagues that were interested in doing a dark matter search. And so essentially the idea here is that for certain axion dark matter models, either through decay or annihilation, the axion can give rise to a radio line at the frequencies covered by the GBT, and essentially by looking on directions that correspond to forward and backward in the Earth's motion around the galactic center, and that correspond to directions inward and outward towards and away from the galactic center, that you can sort of do a cumulative analysis and add up all of the data from the Breakthrough Listen archive in those frequency ranges and see if you see the kind of offsets due to the rotation shown in the bottom left plot, or the increase in dark matter density towards the galactic center compared to the direction towards the galactic anticenter shown in the plot that's in the bottom center there. And they can put pretty tight constraints on models of axion mass and cross section. So it's been really cool. This was with no additional observation with the GBT, to see what they've been able to do with the data that's in our archive.
Okay, we're running out of time, but let's deal with one last question. Are the large Starlink-like satellite constellations a significant problem?
That's a good question. I think they're a significant problem for radio astronomy. Some provisional analysis by my student Andres this summer suggests that we're not seeing a lot more hits at the top end of X-band in the frequency ranges and at the frequency resolution that we're looking at. I think that's probably not universally true of people who are doing observations that rely on more kind of broadband and perhaps shorter integrations at those frequencies. But I think over a 30-minute cadence and at the frequency resolutions that we're looking at, we haven't seen a dramatic increase in signals that we can isolate to Starlink. As I showed in that plot earlier, we do see signals from the geosynchronous satellites, but I think maybe part of this is just that the Starlink satellites in low Earth orbit are relatively fast moving and so are not affecting our data all that much. Still good motivation to coordinate with Starlink and with other satellite providers to do things like the National Radiodynamic Zone prototypes that are being tested at GBT and elsewhere at other NRAO and at the ATA as well as other sites.
Thanks very much, Steve. That's all the time we have today. Let me remind everyone that this has been recorded and will be available on the Green Bank Observatory website within a day or two. Please join us 2 weeks from now, where Anish Roshi will be speaking on detection of helium recombination lines in the Cygnus X diffused ionized gas. We hope to see you then. Thank you and goodbye.